Okay, section 8.2 is areas in the plane. So basically a plane is one-dimensional surface. So we're looking at areas that are a little bit more complex than what we're looking at. They're between 2 or sometimes 4 different lines, depending on what's going on. Generally, because it's still an area, you're looking at all of the area between 2 different lines. So we're going to look at how to do that through integration. Again, don't worry about these ones. There's a new list at the bottom of this lesson. Okay, so if there's more than one curve and you want to determine an area, we want to determine whether it should be integrated with respect to top-bottom, which means it's in terms of x, and this is always going to be kind of our default way of thinking. So see how if I want to draw those little tiny baby rectangles, they can all fit like vertically in there, right? In between, like touching the top line and the bottom line, okay? So that's our kind of default, in which case the area is going to be in between whatever our boundaries are. So in this case, a and b, the integral from a to b of whatever the upper function is minus whatever the lower function is. Because the upper function is actually going to get us everything under there. And then the lower function, we're subtracting all of this. Okay, so then we're just left with that shaded area, okay? So that's how we would do it in terms of x. If we look at it and we say, okay, if I was starting to draw my rectangles, see how this chunk here, it's between the same line, okay? And then we've got these weird boundaries and then like weird bits where there would be 2 rectangles here. So this doesn't really work in terms of x. If we like just rotate this, now do you see how I can draw my normal rectangles all within those 2 lines, okay? So in this case, we're integrating with respect to left and right, which means we're just looking at the function in terms of y. Okay, so if I have the function y equals x, right, which is just the straight line like this, in terms of x, it's like this. In terms of y, we just isolate for x and have x equals y, okay? So our x coordinate now is given by whatever our y coordinate is instead of the opposite. If we had something like this, where we have x squared, right, y equals x squared, we could say, well, x is the positive or negative root of y, okay? So that's basically getting things in terms of y, where y is now our variable that we're plugging in. So it's basically switching which ones are independent and dependent variable. But in this case, if we do the area from the function on the right minus the function on the left from C to D. So see how like my boundaries fit better that way? So I'm adding up all of the little rectangles this way from C to D in between here and here. So I'm taking all of the area left of this and then subtracting all of the area left of that. Okay, so we'll do an example like this. You guys will get to see what I mean. This is how most of our examples work. This is for the cases where this doesn't work. Okay, so determine if the area is 1 or more regions and set the boundaries of integration, and we're going to use the evaluate the area using 1 or more regions. Okay, so all of that will make more sense once we actually do some. So our first one is we're going to determine the area between y equals x and y equals x squared and y equals root x. So the first thing I'm going to do is I'm going to draw the graphs of these. So we know x squared. I'm going to go 1 and 1. So I'm going to actually plot some points on this so that we get like an accurate graph. So there is y equals x squared. And then the other one we want to do is y equals root x, and we know that that's going to be above that. Okay, so there are our 2 graphs, and we could confirm that by graphing them. So basically what we want is the area in between the two graphs. Now in this case, it doesn't need to give us like an A value and a B value like it did for this, because the two graphs intersect twice and it gives us a really clear area between them, okay? So we're gonna do the integral from, we know that this first intercept happens at 0 and our second one happens at 1. So we're just integrating, we're adding up all of the little pieces as we move across as x gets bigger and bigger and bigger and bigger. So this one's just our normal in terms of x. We're adding up the tiny little chunks of dx, right? So because the root x is on the top, we're gonna put it first and then we're gonna subtract x squared, and we're adding up all those little baby dx's. Now these ones are easy enough that we can just integrate each of them through the antiderivative, which all of these will be. So this is x to the 1/2, remember. So x must have started with a 3/2, so that when we subtract 1, we get a 1/2. And then if there's a 1 coefficient out here, then it must have started with a 2/3, because then that 3/2 would drop down and multiply with it to give us the 1. And then same deal here. So if it starts as an x, or it's now at an x squared, the antiderivative must have been an x cubed, and then there would have been, sorry, a 1/3, not a 3. A 1/3 that 3 would drop down and multiply with. And then we're going to evaluate all of that, put in brackets, from 0 to 1. So it's going to be 2/3 1 to the 3/2 minus 1/3 1 cubed minus 2/3 0 to the 3/2 minus 1/3 of 0 cubed. So this whole thing is 0. 2/3, so this is 1 to the 3/2 is just 1, so this is just 2/3. Oh my gosh, struggles. 2/3 minus 1 cubed is 1, so this is 1/3, and then minus 0. So 2/3 minus 1/3 is 1/3. So we have 1/3 units squared of area in between those two lines. Okay, so it's using our integrals and then trying to figure out, okay, how do I need to set it up? Which one's top, which one's bottom, and then how do I get that area in between? The next example is determine the area between y equals x times e to the negative x squared, and then y equals x plus 1. And then our other line, that our boundary is x equals 2. So I'm going to draw out the first couple and we'll talk about why we need that other one. So y equals x plus 1 is just a straight line like that. So there's our y equals x plus 1. Right, our intercept is up at 1 and our slope is 1. Then our x times e to the negative x squared, I had to actually graph that, and it kind of looks like this. X to e. So that looks like that. So now we need actual like points to figure out, okay, where do we want the area between? So one of them is x equals 2, so let's just say that that's there. And that becomes one of the boundaries for our area, and the y-axis is our other boundary. So we're looking for, I guess I could draw them as our little rectangles. We're looking to add up all of those little rectangles in that shaded area there. Okay, so it's going to be the integral from 0 to 2, because from the y-axis to the line x equals 2, that's our boundaries. As far as our little dx's, we only want the dx's in between those. So then our top function is the x plus 1, and then our bottom function is the x e to the negative x squared, and then all of that gets a little dx. Okay, so if we want to, I guess we don't need the integral. So this first one, this is easy to integrate. So it's going to be, if we started with an x, or if we end up at an x, we must have started with an x squared, and there must have been a 1/2. And if we end up with a 1, that must have been an x. Okay, so that part's easy. Then to do the integral of this part is a little bit trickier. We're actually going to use a substitution. So off over here, we're just going to draw ourselves, we're going to give ourselves a u. So what I see here is a complicated exponent. So I'm going to say u is equal to that complicated exponent. And then my du, and then it would be over dx, but we're going to move that over. My du of this guy would be the 2 comes down, so 2, -2x, okay? And then if we had the dx over there and multiplied it over, so it would give us a -2x dx. So notice how that x here, we can rearrange this. We've got e to the u, and then we've got an x dx. We just need to get rid of the -2. And now we can plug this and this into that equation. Okay, so the integral of e to the u times du over -2 is equal to, that -1/2 can come out, and then e to the u du is just e to the u. Okay, then we can plug our -x squared back in, so 1/2 e to the -x squared. And that can go back up into that statement. So it's going to be minus -1/2 e to the -x squared. And this whole thing is going to be evaluated from 0 to 2. So we're going to have our top boundary plugging in first. So 1/2 times 2 squared plus 2 minus a negative turns that into a positive. So 1/2 e to the -2 squared minus, now I'm plugging zeros in. So 1/2 times 0 squared plus 0 plus 1/2 e to the -0 squared. So this, we've got 2 squared divided by 2, so 2 plus 2. This whole thing, now we've got -2 squared. Notice how the -2 is not in brackets, so it's going to be an e to the -4. So it's going to be 1/2 e to the -4. This term cancels, that's a 0. And then this is a -0 squared. 0 squared is still 0. Anything to a 0 exponent is a 1. Okay, so e to the 0 exponent is just 1. So we're going to leave that 1 over 2 e to the 4. And then we've got 2 plus 2 is 4 plus a half. So 4/2. Oh wait, sorry, this one's a negative. So that negative would distribute in. Let's fix that. So 8/2 minus 1/2 is 7/2. Okay, so there's our area. The next one is determine the area enclosed by y equals sine x and y equals cos x, x equals pi over 2, and the y-axis. So again, we're going to have like boundaries on this one. So we're going to just draw those two graphs. So we know that at pi over 2, we know that sine, so let's just do them one at a time. So y equals sine x at 0 is going to be 0. And then at pi over 2, that's where we're going to have our maximum. Sine of pi over 2 is 1. So then I can kind of draw in my wave like that. cos is going to be 1 at 0, and then at pi over 2 it's going to be its minimum. So then we can kind of draw in a wave like that. Okay, and then the area enclosed by these two lines, x equals pi over 2, so that's one boundary, and then the y-axis, that's the other boundary. So we want all of that area there. So this time, because at this point, and we know that because these things are symmetrical, this is going to be halfway in between, so pi over 4. And we also know that sine and cos are equal to each other at pi over 4, right? They're both root 2 over 2. So that point is an important point. Because now, for the first half that we're looking at, this is y equals cos x. This one's y equals sine x. Cos x is on the top. So if we do the integral from 0 to pi over 2, notice how they switch which one's on top. So I'm going to make this one a little bit darker just so we can see. So here we have cos x on top, and then here we have sine x on top. So if I just did from 0 to pi over 2, I wouldn't know which one to put on top because it switches. So I'm actually just going to integrate each separate chunk. So for the first bit, we're going to get an area, and then we're going to add it to a new integral for the second bit. So this one we're doing cos x, the top one, minus sine x, the bottom one, dx, plus the integral from pi over 4 to pi over 2. Now we're doing sine x, the top one, minus, cos x, the bottom one, dx. So now, when we do the integral, we can just do it as each individual term. So the integral of cos is sine x, and then the integral of sine is negative cos, but we're doing negative sine, so it's negative negative, so it turns into a positive from 0 to pi over 4, plus the integral of sine x is negative cos x, and then the integral of cos x is sine x, but there's a negative out in front. And then from pi over 4 to pi over 2. So now we're just going to plug those things in. So we're going to do sine of pi over 4 plus cos of pi over 4 minus, put those in big brackets, minus sine of 0 plus cos of 0. Okay, so that's this section, and then plus this part. So now we're doing negative cos pi over 2 minus sine of pi over 4, no, pi over 2 still, we're doing the top one. And then minus negative cos of pi over 4 minus sine of pi over 4. Okay, so we're just doing each integral as its own thing. So now we just need to simplify. So sine pi over 4 is root 2 over 2. Cos pi over 4 is root 2 over 2. So that's my first square bracket. Minus sine at 0, remember, so here's 0. It's the coordinate 1, 0. This is 0, 1. So sine at 0 is 0. And then cos at 0 is 1. And then plus negative cos of pi over 2. So cos here, that's negative 0. And then we've got minus sine of pi over 2, so minus 1. And then minus this guy, so negative root 2 over 2 minus root 2 over 2. Yep. So this is 2 root 2 over 2, so that just simplifies to root 2, minus 1, minus another 1, and then minus negative, so that turns into plus another root 2. So we get 2 root 2 minus 2. Okay, so that's the area in between. So we had to flip our integral halfway through, like which one was top, which one was bottom, because of the nature of these two lines this time. Okay. Our last example is we want to determine the area between y equals plus or minus root 2x plus 3. So the plus is here, and then the minus is this part here, which is super, super faint, but there it is. And then y equals x minus 1, so here. Okay, so this is one of those ones that if we turn it, we can draw nice little rectangles that touch the top line and the bottom line. Okay, so we want to do this with respect to y. Okay, so this is with respect to y. So y is our variable that we're integrating with instead of with respect to x. And we're going to do it from y equals -2, where that intersect is, to y equals +4, where that intersect is. Okay, so the first thing that we need to do is get things in terms, get the equations as x equals blah, 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 instead of y equals, because then it's in terms of y. Okay, so y is going to equal plus or minus root of 2 times x plus 3. So we want to isolate for x. So the first thing that we're going to do is square both sides. So then we're going to have y squared equals 2 times x plus 3. Divide both sides by 2, y squared over 2 equals x plus 3. So then x is equal to y squared over 2 minus 3. Okay, so that's one of our equations. And then the other one is y equals x minus 1. This one's much easier. So x is equal to y plus 1. Okay, so now we want to set it up as the integral from, again, -2 to +4. And we want to take, I just like turn it, right? So we now know that the one on top is this guy here, the y squared over 2 minus 3. And then the bottom is our x equals y plus 1. Okay, so we're still doing top minus bottom. We just have to rotate everything 90 degrees to do that first and get everything in terms of y. So we're still doing top, so in this case y squared minus, or divided by 2 minus 3 minus bottom y plus 1, and we're integrating with respect to y. So we're breaking y up into those little tiny chunks, right? Which is why they are horizontal lines instead of vertical lines. But the rules here are the same. Integration the rules don't change depending on what variable you have. You're now just integrating y's instead of x's. Okay, so we're going to do this one. So y squared divided by 2. This must have started as y to the 6, or sorry, not y to the 6. I'm getting ahead of myself. Y to the 3. And so when that 3 drops down and multiplies and turns it into a half, it must have started as a 1/6. Okay, and then minus 3, that must have started as a minus 3x. It's not an x, it's a y. And then I'm going to distribute the negative in first before I integrate, because that just seems easier. So we're integrating -y, so it's going to be negative y squared, and there must have been a -1, or there must have been a 1/2 for that 2 to come and multiply with. And then we've got -1, so that would just be a -y. And we're going to evaluate all of that from -2 to 4. So now we're just, I'm going to combine this because this is -4y, which seems easier. Okay, so I'm going to write that over here so I don't run out of room. So this is y cubed over 6 minus y squared over 2 minus 4y from -2 to 4. So now I'm just plugging these guys in. So I'm plugging a 4 in. So 4 cubed over 6 minus 4 squared over 2 minus 4 times 4 minus -2 cubed over 6 minus -2 squared over 2 minus 4 times -2. So it's important that these negatives go in as brackets, but you guys are good on grade 9 math, so I trust that you're doing it. So this is 64 over 6 minus 4 squared is 16 divided by 2, so that's -8, and then minus 16, and then minus, this is going to be -2 cubed is -8, so that's going to reduce to -4 over 3. And then -2 squared is 4 divided by 2 is 2, and it's negative. And then this one is a +8. Okay, so we add all of those things up. We need a common denominator. So we get -18. So these guys are, there's a whole bunch of negatives in here. Remember that we're distributing. So we get a -18. Now, the reason that it comes out as a negative is because we actually reversed the way that we did our integration. So if you go back to the page where the definitions are, it's always going to be the right function minus the left function, and that's like the way that this thing is defined. So this is the rule. Now, when we do this, I just find it a lot easier to relate to what we know, where we're integrating from the left to the right, from -2 to +4. That makes sense. And so we're doing top minus bottom. But technically, it should be bottom minus top when we're doing it a sideways. It should always be right minus left. Okay, but I just always do it the way that makes sense to my head. I actually physically turn it. I go from -2 to 4. I do top minus bottom. And then I know whatever I get, I'm going to have to flip the sign. So then I just flip it to a +18. That makes sense to me to do it that way, but you could have always done, you could have switched here, because we did left minus right. You can just always know right minus left is the way that it should go. Okay, so this is like the definition. I find I can conceptualize it more if I do the opposite, and then absolute value, or like flip the sign of whatever you get. Okay, so a couple different ways to think about it. You can always go by the actual definition of it if you prefer that. Okay, so there are your practice questions for today. Most of them are with respect to X, but some of them are with respect to Y. Okay, the ones that we can do with respect to X, or they can all be done either way. They're just going to be easier one way. Like this one could have been done saying, okay, from -3 to 1, we're doing the top as the positive version and the bottom as the negative version. And then the top here is this positive version, and then the bottom here. So it could have done 2 separate sections of 2 different integrals. I just find this is easier. But there's lots of different ways to do these things. So yeah, there's the practice questions. Let me know if you have any questions.